This is the midterm demo for the solar-powered UV water cleaning and analysis system. The system was designed and presented by Group 5, which consists of Kendra Kordack, Bradley Blackburn, Grant Cooper, and Lucas Heredia. During this presentation, we are going to show where we are at in our development process and various problems and solutions that we're coming up with as we go along. If you are not already familiar with this project, it is a UV water cleaning system that also analyzes the clean water via Raman spectroscopy. We went with a dolly setup in order to keep a semi-portable profile. At the bottom, we will have our batteries resting. In the middle is our wet panel. This will house our filtration system and spectroscopy equipment. And at the top, we have our electrical panel. This will house our user interface and control systems. The system will also have off-grid operation, meaning that it will be powered via its battery, and the battery will be charged via solar panel. Here are the specifications for the project. The first three are our main focus, and these are the ones that we will like to demonstrate in our final project. For the power supply and solar power system, it should offer at least 8 hours of off-grid operation. It should successfully recharge the battery, and the battery will be a 12-volt, 75 amp hour battery. For the water analysis, it'll be done through 785 nanometer Raman spectroscopy. We should be able to interpret the data from the water, and we will also be monitoring the temperature of the water with an infrared temperature sensor. For our user interface, our goal is to have control over the system with our LCD display, and then it should also show feedback of parts of the system. For our water quality, we want it to have as little to no benzene, cyanide, and arsenic, which we will attempt to look for via the spectroscopy. And for the water filtration, we have a Class C UV lamp, one 5 micron sediment filter, one carbon filter, and it will be running at about 2.9 gallons per minute. Here is a progress chart from our last CDR video of our plan for the semester. So far, we have completed 5 out of the 9 tasks to be essentially finished with the project. We've tested the spectrometer and light source. We've programmed the spectrometer. We've taken our first reference spectra of the water. We've built our dolly frame, and we've built our wet enclosure panel. The next pieces that are still being worked on are the software and the user interface, the electrical panel, which is in its prototype phase, which will be changed. The integration of the whole system is still being worked on, and the final testing needs to be done. Following this slide, we will begin testing various components of the system and demonstrating how they work. This is our first prototype electrical panel for our solar-powered UV water cleaning system. Right here we have a 12-volt DC supply, which will be acting as the battery in this demonstration. In the final design, the battery will be connected to this charge controller, which will charge the battery via solar power. Here we have an Opto22 booster module. This will boost the output from the Raspberry Pi in order to flip a relay to turn on the respective component. Up here we have our voltage regulator, so it's a 12-volt voltage regulator, 24-volt regulator, and a 5-volt regulator. This is our PCB board. In the final design, these will also be replaced with our PCB boards. They are still on the way here. They are designed and finalized already though. For this demonstration, I will be flipping this little switch up here. This will simulate an on output from the modules to run each component. So first, I will demonstrate the pump running. Here, I will flip this, and as you can hear, the pump is running. Flip that down. Next is the UV system. If you go down here, you can see the UV turn on and turn off respectively. For the temperature sensor, the temperature sensor is not hooked up yet. So what I will do is I will hook this to a ground, and I will demonstrate that the output shows a 24-volt output. Put that on, touch it, and indeed we have 24 volts. Lastly, I will be testing our infrared laser for the spectrometer. So I will turn that on, and with this card you can see the laser is indeed on. So far this has worked good. The only issue that we've had is that the pump needed to be rewired straight to the battery source, because if it was running off the 12-volt supply, it drew way too much current and it would actually turn this module off momentarily, which in turn would probably stop the program that we have set for the system. Other than that, now that the pump is hooked up correctly, as you can see, there's no interruption of the signal, and this should work very nicely once we have our GPIO programmed.
So here is the spectroscopy system connected to our filters. It shows that the laser is working through the entire system and into the spectrometer. The spectrum that we're getting is at 785 for the spectroscopy system, which shows that we're getting the right peak. All that we have left to do is take base spectras and make sure everything is perfectly aligned.
This is a basic spectra of what we got with the system just going through air. This is a spectra we got from putting a water bottle filled with water in the middle of the system. We are still trying to figure out how to interpret this data. For the spectroscopy system, we still need to take base spectras with filtered water, unfiltered water, and arsenic in water before putting the entire system together. Then we need to interpret the spectra data so it is easy to understand.
Hi, so originally we thought about connecting the spectrometer directly to the Raspberry Pi and using a software developed in Java to control every aspect of the spectrometer. The software would look like what Ocean Insights has. The software the Ocean Insights has called Ocean View, and Ocean View controls the spectrometer data and displays it to the user. But we were not able to do that. First, because Ocean Insights did not give us the library to control the spectrometer. They just gave us Ocean View itself in order to control. We also had a problem with the GPIO library running on the Raspberry Pi, because this Raspberry Pi is a new model, and the open source library used to control Raspberry Pi GPIOs is not yet developed for this specifically Raspberry Pi. But still, we were able to design the UI using JavaFX. Unfortunately, we had to scrap the previous design, and now we have the spectrometer connect to a completely separate computer. And because we're not even to make the spectrometer run in the Raspberry Pi just using Ocean View, because Ocean View is not compatible with Linux, and that's was a big issue. So now what we have is the Raspberry Pi just responsible for the other sensors, including the pump and the temperature sensor. But we're still using JavaFX as the design for the UI. And we are able to solve the GPIO problem by using a separate software I call in this slide software 2, and it's basically a script run in Python, And what this does is it creates a database and just creates this database and controls the GPIOs. And whenever it changes something in the GPIOs, it sends to this database, and the database will communicate with the UI, and the UI software one will update it based on the information that it gets from this database. This database is implemented using SQLite. So we have a couple of problems and some options how to solve them. So first of all, there's no reason for us to continue using Java. The reason why we began is because the spectrometer is more compatible with Java. Its libraries were written in Java, but right now only our UI is written in Java, and there is a compatibility issue with Java effects. I'm not being able to run it in the Raspberry Pi for some reason in the Linux system. So we can either redesign the whole thing in Python and make it a completely new UI, or I can continue to try to solve this compatibility issue. Another problem that we're having is the temperature sensor, interfacing the temperature sensor with the computer. The temperature sensor, different from the other sensors, is that it works as it sends a current signal, and this current signal cannot be interpreted directly to the Raspberry Pi because there is no analog pin available in it. So in order to interpret this current signal, we probably need a separate microcontroller or a chip to analyze the signal or convert it to a serial signal so it can be interpreted to the Raspberry Pi.
The general purpose input and output pins for the Raspberry Pi are being programmed as we speak. We have a simple code that will turn an LED on intermittently, and this will be translated and enhanced in order to send an output signal to turn on various components of the system. There was a video showing this simple task, but it was not recovered by the time this presentation was needed to be turned in. But we would like to address the fact that this is being worked on, and this will be used in order to turn on various components of the system and operate the system via the user interface.
A crucial part in our design was creating the PCBs for the voltage regulators. We have a 5 volt, a 24 volt, and a 12 volt regulator. We decided to use separate PCBs for each regulator. This was so that we could have the regulators directly at the source so that there would be no voltage drop over the wires, taking them from the PCB to the components. Our laser is a very sensitive component, so we don't want to deal with the voltage drop in the wires. Also, our 12 volt specifically is handling a very high amperage, up to 12 amps could be passing through that PCB, and that's going to be generating a lot of noise. So we really wanted to separate our regulators from that 12 amp so that it didn't disturb the processes on the other regulators. We decided to go with 0805 parts due to COVID and uncertainty of how we're going to get our design soldered. So we wanted to have parts big enough that we could solder ourselves. A trend that you could notice in PCB design is that as the max current increases, the complexity is going to increase as well. With higher amperage, you're going to have to make much more thermal considerations, trace considerations, and laying out the ground is going to take a lot more effort than in lower current applications. So the reality of WebBench Power Supply Designer, they say on their website, spend 30 minutes with us and you'll have your completed PCB ready to go. That's not really the case. When trying to upload library files from WebBench to Eagle, there are errors in the parts for all 3 of our regulators. So it's really recommended that WebBench be used as a schematic generator. So we used WebBench to get our schematic, and then we took that and used it in Easy EDA, and we were able to create the 3 voltage regulators you'll see soon. Our 5 volt, 5 amp regulator was developed on Easy EDA. We gave it to QMS to solder it, and they tested it first try. It worked. Happy days. Some important things to note is that under the IC there are thermal vias to help spread that heat throughout the whole PCB. Also, we use ground planes for the input and the output rather than traces. Pretty much the wider the ground plane, the better our PCB can handle that high amperage. So that was very important in our design. If you look on the right, we supplied our regulator with 12 volts in, and we got 4.99 volts out. If you account for a voltage drop in the wires, then that value is pretty spot on, right at 5 volts. So we were really happy with this design. Here's the PCB for the 24 volt 0.03 amp regulator. We used Easy EDA to develop it and brought it to QMS to solder it. So we ran into some complications with QMS. QMS lost the IC. If you look closely on our PCB, there's the TPS, that's the IC, the brains of our chip. They lost it, so we got delayed in that. I had to go bring them another one. And then when they finally did finish it, the engineer came and told me that the IC was overheating and that they were getting no voltage on the output. And so I was really discouraged by this. I was thinking, okay, I'm going to spend the whole weekend redesigning my PCB. And then I looked a little closer at the diode. You can see the diode on the bottom right, and they put my diode on backwards. So no current was able to flow to the output. That's why there is no voltage, and that's why there is the IC heated up a lot. You can see in the document that I gave them, I literally said right side is the negative. You can see that that strip is on the right side and it has the minus sign. And then if you look below that, you can see that that little line that indicates the negative is pointing the wrong way. So I'm going to be bringing this PCB back to them on Monday morning. I'll probably already have done it by this presentation, and hopefully they can turn that die around for us, and hopefully none of the other components on the chip got corrupted by running it wrong. I also have a complete copy of the PCB and all the components, so I'm going to give that to them as well. So I'll have 2 boards, and even if the first one was corrupted, this second one should have no problems if they wire it correctly. So that's where we're currently at. Finally, we have the 12 volt, 12 amp regulator. I like to call this guy the big enchilada because it has 46 components, much more than the other 2, and higher amperage, so you need to be much more careful in laying everything out. If you look on the left side, that's the schematic that we generated using WebBench Power Supply Designer, and then we kind of use that as a guide, so we created that in Easy EDA. And then on the right side is the PCB on the top. That's the top copper layer. And the most important thing to note about this is that if you see that little encapsulated area kind of surrounded by the rest of it, that is the analog ground plane. And so it was very important to keep our analog ground plane separated from the power ground. The power ground is going to have a lot of high amperage, creating noise, and that noise would disturb our analog signals. So that is why it's laid out that specific way. This design took a little bit longer than the other 2, so we're currently waiting for it to be delivered to us, and then we're going to take it to QMS to solder it.
As you can see, the system is mostly up and running separately, not as a whole, so that will be our next venture is putting it all together. Also, we will need to build and finish the software and user interface, as we might have to restart on the user interface because of compatibility issues. We are going to build the finalized electrical panel. The finalized one will have all of our PCBs. It will be a little bit larger, and it should offer control and operation of the system. Also, with this being done, we should be able to integrate the whole system, where everything should be talking to each other. We should have control over the system, and it should be operating on its own. And then lastly, we should be able to test. We want this done by November 20th of 2020. This is when our conference paper is due, and this would be an optimal time to finish the project. Thank you for watching.